So you're all in rank position. Pretty cool. See what else we got. This is the other one. It is relevant to fluid mechanics, as we'll talk today. Just wait till we get up to 8 o'clock even. Good enough. Well, let's maybe get rolling. I guess the other big news of today, of course, is Florence coming on shore with tidal surges, etc., and lots of high winds. And maybe it actually fits into what we'll talk about today, because what we'll talk about is we've already introduced Bernoulli along a streamline. Now what we'll do is we'll talk about going perpendicular to that streamline, and that's only important and interesting to us if the flow is in a rotation, such as in a hurricane or as in a jaguar doing a loop. It's basically the same processes. So those are the couple of things that we'll talk about today, both along a streamline and normal to a streamline. But before we do that, is there anything we need to take care of regarding the organization, if you like, of the midterm? It's a week Wednesday. Well, this coming Wednesday. It's in 108 Forum. You've already got the email. You can bring a two-sided sheet of paper, letter size, of course, and a calculator. Should probably wipe the calculator, but no one will check that. It is a 90-minute exam, like the ones you'd have seen online. You can stay as long as you like, well, almost as long as you like, till midnight, 4 hours if you so wish. We ask that no one leave before 9:15, and that's because people may be coming from PNG lab class, which finishes at 9, and or an EMEC exam, which also finishes at 9. For those people who have conflicts, I guess you should have broadcast them to me on Wednesday, a week ahead of the exam, but I guess we're probably a little bit lenient with that. If you do have this conflict exam in EMEC, my preference, and perhaps I think the best thing for you also, would be to either come late for the exam at 9:15 or a little bit later, to take a conflict exam for the EMEC exam, or to take a conflict exam for this exam, in that order. I say that, it's better for us if we do that, because this is a big class, and it's in your major. If you're in this class, you're definitely in the major in our department. And also, it's predictable, right? So you know to some degree what the material is on the scheduled exam, but all you know about the makeup exam is that it's taken from these materials 1.1 through to 4.1. And so it largely follows these areas, but not exactly in terms of what it is. So that's kind of what we'd hope for that. So if you're in that predicament, you need to contact me. Otherwise, I always get emails at 4 o'clock on the day of the exam. Feel terrible, okay? Get a doctor's note, take the conflict exam, but make sure that you document what is wrong with you before we apply your grade, basically. I've hit a deer. Actually, the guy did bring a police note of having hit a deer, so I thought that was interesting. And so anyway, so you've been through this all before. So I'll stop doing the talking. Any questions about process, protocol? It's not a particularly great thing to talk about. The reason that 75% of the grade, of course, is on the exam is that it guarantees that it's your work, and that's important, obviously. Okay. All right. Hearing nothing? Fine. Okay. So, well, we just looked at some videos, and they kind of reinforce some of the things that we've talked about so far. So I guess the other thing I'll make a comment about is that the homework assignment, which is nominally due, is live today and nominally due on Thursday, in any exam week is due on the Sunday. And so you can put that out of your mind, and it just cuts you a break. So there's some rationality, I think, to the way that we do things in this class, and being able to allow you to present your best work, I think. Also, I keep on getting emails of groups putting themselves together. For some reason, every time you send a group email for group 22 wanting to get together, I get it, I think. I'm not sure why. I'd like not to. So I'm fine to do that. Just you need to be aware that I get it, so you can choose what you put into that email. And so far, I'm sure everything is just fine. Okay. All right? Okay. Well, we're rolling. So just to recap from last time, what we did was we took these equations that represent the change in fluid pressure at a point, both in static fluids and accelerating static fluids, and we changed it into something that we could use along a streamline. We said that we could look at behaviors both, I look at an airfoil, we could look at behaviors as they come, and we could look in two modalities. One is the velocity along a streamline, and also on adjacent streamlines. We could go normal to that streamline, and we could look at the change in behaviors as we went from upstream to downstream to across stream. And at least for this case, we could write Bernoulli's equation as we did. And if we write it out in longhand, as we will typically do, in this order, then we have pressure divided by unit weight. We have velocity squared over 2g. And we have elevation head. This is just, I guess, dividing both sides through by g in this particular case. And we can write it constant, so we can write it at an upstream location, and we can write it at a downstream location. Exactly the same expression. And we can solve for the two locations that we have. And hopefully, since we have an expression which has 6 terms, we hope that we have 5 terms, so that we'll end up with one thing that we can calculate. So last time, I think we wanted to know what the pressure was at the downstream location where it hit the truck. And we could get that pressure by setting the velocity here to 0 at stagnation, one of the things we'll spend some time talking about today if we get to it. And we could calculate the magnitude of the pressure at point 2 as a result of that. If you look at the jetpack that we just looked at, I don't know if we need to look at it again. It's easy enough to do that. Then it's not so different from what we had before, in that you have a fluid velocity coming out of the jetpack. It's not so different from a jet engine. It's a chemical reaction, or it could be just, I think it's combustion, and it provides a velocity of a mass which is moving, and that velocity of mass hits the ground. F equals ma, acceleration is dv dt, and so of course really what we're doing is we're writing the expression F equals ma, which is equal to mass times change in velocity with time. We're writing that as this, just by including this in this term. It doesn't change, and it's the rate of change of momentum. You have momentum, you change momentum by having the air stop against your chest. It provides a force, that's a reaction. And that's really all Bernoulli is telling us about that situation. So in this particular case, the jetpack would be just this. It would be a velocity that's coming out of here, and it would be a pressure which is generated on this surface here, just like on the truck. And you could do a little free body diagram that could allow you to take the pressure that you apply here and say exactly what the force is that's being applied on the top to lift the person up. It's that destruction of momentum. So Bernoulli is just a manifestation of F equals ma. So what today we'd like to talk about is the other aspect of that, and that is that normal to a streamline, we know that the force is equal to mass times centripetal acceleration, which is equal to mass times a velocity theta squared over a radius by which it turns. And so that's kind of relevant to this other example with the car, which you've seen, but let's just go through the meat of it again, because it's kind of interesting. And that is that the car going around this circuit is going on a circular trajectory. And you could imagine that you were sitting in that car, you would be pushed into your seat as you go around that because of the centripetal acceleration. You're being pushed out by centripetal force. The car seat is resisting you in your butt, and you feel that. Also, the fluids in your body would react to that as well, the static fluids in your body, in the same way that we talked about for the case of a rotating container. And so that is behavior that is looking at the forces applied normal to a streamline. So in other words, as you go out over here, if the streamlines are parallel to each other, then it's not really centripetal force because the radius is very big, and therefore there is no, as this becomes infinite, then this angular acceleration becomes very small. But as r is smaller, such as in a curve here, then that component becomes substantial. And so it's also relevant today for Florence, of course, because if you look at Florence, I mean, the reason for a hurricane, I'm not sure if I can draw this very well. That's the globe. That is a line of longitude. And that is a parallel line of longitude. If you look at the rotation of the Earth, which is going at some angular velocity, then the velocity that something, if this is the center line coming down here, the velocity of something that is traveling at some high latitude versus a low latitude, R2 is going to be larger than R1. And we know that the velocity theta is equal to a constant omega times the radius. And so by definition, this velocity here of the Earth going round is going to be faster than this velocity here. The air is sitting above it, static if it would like to be, but acting on the bottom of the air is the Earth, which is going at some velocity, v theta, underneath it. If it's going at this velocity, then you'd expect the distribution of velocities in the atmosphere to vary something like this. If this were velocity and this were elevation. And we know this because, for instance, Newton's law of viscosity is that the change in velocity with y, we said, but z in this particular case, is proportional to the slope of this line. So there's some force that's applied on this, which is a shear stress. And so the shear stress at point 2 has to be greater than the shear stress at point 1. And so if you look at a block of fluid which is sitting there, this is tau 1, this is tau 2, and this is the extra tau stress that is applied on the bottom, which, if it's not checked, is going to be rotating it. And so that's the reason that hurricanes will rotate by the surface of the Earth. And so the pattern that you get around a swirling hurricane has to be counterclockwise in the northern hemisphere, and you'd expect it to be clockwise in the southern hemisphere for this reason. And so the mechanism by which it acts is that in the center of the storm, we already did this, right? You have hot water. Hot water causes the density of the fluid as it heats up to expand, density decreases, because we know from the ideal gas law, if we just rearrange it, that it's equal to P RT. Pressure doesn't change because the pressure inside the hurricane and outside the hurricane have to be the same. If the temperature increases, the density increases. If the temperature increases, the density decreases. The density decreases compared to the density here, then it rises. If it rises, it has to replace fluid here, and you get this circulation at the same time that it's rotating. And so that's kind of the mechanism by which the hurricane will occur. So if this pressure is reduced by the fact that this is rising, which it is, if you drew a pressure distribution across here, and we did this example already, then you'd find that the pressure in the middle of the storm is low, the low pressure here and high pressure outside, as you see on a weather map in plan view. Then this magnitude here is something of the order of, this is 1,000 millibars, 1 atmosphere in other words, and this, the lowest ones might be 800 millibars, not 8,000. And so if you look at the difference in the pressure acting here to the pressure acting here, it means that the water level that would be beneath this would rise, and you can calculate the magnitude of that rise from delta P is equal to H gamma. And so as we calculated before, if this is 200 millibars difference, this would be 2 meters. If it's 100 millibars difference, which is more usual, that's quite a deep storm. This is a tenth of an atmosphere, 10 kPa in other words, then it rises 1 meter. And so we know that the storm surges that are expected are something like 15 feet or something, so clearly that can't be the whole story. So the other part of the story is that in this storm turning clockwise, is it will basically bulldoze water onshore here and be pulling water offshore here. And so the storm surge at the top part of the rotation is always going to be large enough. So this all relates to what we're talking about in terms of fluid mechanics. So that's kind of what we, if you like, to give context to what we were talking about today. Let me clean this up. Okay. So how do we deal with this? Well, what we know is that in the same way that we've written Bernoulli's equation for linear behavior between an upstream location and a downstream location, in this case, if we look at going across the streamline, so in terms of our storm, it's rotating, we get this behavior here, going radially outwards from one location here to a second location here, where we also have, bless you, a streamline going through at some potentially different velocity. It allows us to say something about how pressure will change across there. we already know a little bit about that, because if you remember what we drew before, what we might expect is that if we have a container that is spinning on its axis at some rotational velocity, then we expect that the original level of this, if you looked at any of the examples, would actually take some kind of parabolic distribution. And the parabolic distribution means that this surface height here, if you plotted the pressure acting on the base of this container, would be the inverse of that. It would be some magnitude at the edges, and it would look like this. This would be the pressure. And so in the same way that we expect this to be low pressure and high pressure, if it's a storm, this would be low pressure and high pressure. And so part of this rotation contributes to the deepening of the pressure within the storm as it rotates faster and the winds get faster. But also part of it is just by buoyancy of the air leaving as it gets heated up and having to suck in other fluid. By definition, as it leaves, as it gets more buoyant, it makes the pressure less. And this low pressure here results from two things. Not just the centripetal acceleration, but also the fact that we're losing mass by lofting within the system. Okay, so we'd like to be able to figure out exactly what's going on here. So what we can do is we can write Bernoulli's equation normal to a streamline. If we do that, the geometry is pretty straightforward. We've seen it before, but I'll draw it out for you. I think we're only interested in the final result, but I'll do it anyway. I'll do this figure anyway. So this is the rotation. This is the rotation v theta. This is some radius. This is a radial direction, which we'll call r. This is the center of rotation, like for the jag going around the track. This is the center of the rotation, or it'd be the center of this. This is moving at some angular velocity, which we'll call omega. This angle is theta, hence we call this v theta. And do we need anything else? I guess we need to know that this is at r equals uppercase R, and this is at r equals 0 at the middle. And we know that omega is in rotational speed, it's in radians per second. And we know, for instance, that v theta is, we've already used it today, is equal to the radius times the rotational speed. If we know that we want to calculate this, then we know that the rotational acceleration is r squared omega squared divided by r, which is the same as r omega squared. And this is clearly going to be the term that ends up in this expression. You see the manifestation of that already. And so I guess what we could do is we could use, if I remind you that the expression we had before for equilibrium within a rotating fluid is that the rate of change of pressure with R minus, I had to remind myself, rho R omega squared, this term here, is equal to 0. What we could do is we could rearrange that. So we have dP minus rho R omega squared dr equals 0. We could integrate that. And I suppose if we do that, then we end up with, what else do we need to do? We could do things like we could divide this through by rho g, because then this becomes the, in terms of units of length rather than anything else. And if we do the integration, we end up with P over rho g, not unit weight, I guess P over unit weight, is equal to a constant, because we've done the integration without limits. And this would be the term where we'd get rid of this, and we get rid of this, and we'd have integral r omega squared over gravity dr. And no, we'll basically have this expression here. The other thing which I didn't mention, which I should mention, is that we can define a value of r in this direction, but we'll also define a value of what we'll call n. N always points to the center of rotation. N is a unit vector typically. It has length of 1, and it points in towards, in this case by definition, points into here. And so in this particular case, the direction of n is in the opposite direction of r. So dr is equal to minus dn. And so if we substitute for this here, we end up with an expression which is p over gamma. I guess this would be a positive. Well, which is this? This would be a turn to a positive integral r omega squared over g dn. And there would be another term which would go in here, which would be elevation. These are in terms, just this term here. But I'm just going to put that in. So the derivation doesn't matter too much. The fact is that we have an expression which now gives us a behavior which we can now work with. The other thing that we could do, why have I got an extra r, okay, v squared, okay, yeah, okay. And so I guess the other thing I need to make the substitution for is that v squared is equal to r squared omega squared. So in other words, this would be r squared, and then this term here would be the streamline velocity squared. And so the final term should be something like p over gamma plus vs squared. I'll write this as uppercase R times g integral dn plus z equals constant. So anyway, so that's, you'll never have to do that derivation, but that illustrates maybe where this expression comes from. So the provenance of that, I guess, is that this expression here basically comes from, as we found out, from F equals ma. And it's a manipulation of that which gives us this, which is Bernoulli's equation perpendicular to a streamline. And so our interest then is in being able to apply it in some useful way, to be able to say something about how magnitudes of pressures change as you go perpendicular to a streamline. So we don't need to do that, 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 or that, but we'll do this. So let's talk about a straightforward example. And so this is one that allows us to be able to look at exactly what's going on in this system. So you have water that's flowing along. It has some given height. It goes over a bump. You can imagine that if you were running down the road and driving at constant velocity, constant speed, then you'd feel no acceleration yourself. But as soon as you went up over this incline, first of all, you get pressed into your seat as you go upwards, because you're going upwards in the z direction. And then as you reach the crest of the hill and fly over the top of it, you'll feel lighter because you're thrown up in the air and you come down the other side. And so water, if you have water in your glass, is no different. It's like doing a zero gravity turn in an aircraft. If you look at doing a zero gravity turn in an aircraft, then the water just is perfectly aligned with the cabin floor, even as the aircraft is tipped. And in this case, the water within your beaker will see different pressures in it. And so what we could do is we could look to see how the pressure changes as we go across from location 1 to location 2 and location 3 to location 4, and see what we expect to happen in each of these cases. So we've already made the case before, and I suppose we could draw this, is that we talked about this thing called an energy grade line, and that if you look at a point and you look at a datum, then by definition, this length here would be the elevation head. This length here would be the pressure head, the pressure point 1, and this term here would be the velocity head. Right? And that stays constant throughout here. We also drew last time the fact that if you looked at how the pressure changes as you go along this line, pressure versus depth minus z in this case, then we'd expect it to look like this. So at this particular point here, the pressure would be equal to this magnitude here. And it's linear because we know that with here something like this is true. Right? This is just this linear variation. And so that's what we'd expect to happen here. So equally, if this was a static fluid, it's not a static fluid, we should get that result if it's a moving fluid as well. And so what we can do is we can try using this expression that we have here on the top to be able to examine that particular behavior. And so our way of doing it is exactly the same. So we're going to write this expression at 2 points. We want to know the pressure at point 1 because we think we know the pressure at point 2, right? If it's atmospheric and we take gauge pressure as being the norm, then its pressure is 0. And so we can write this expression up here as this. P1, yeah, okay, let's do it. They do it in an example. I won't divide through by unit weights. Let's just do it this way. P1 plus rho integral V1 squared over R dn plus unit weight Z1 is equal to P2 plus rho, the same integral, V2 squared over the radius multiplied by dn plus unit weight times Z2. What do we know? We know that P2 is equal to 0. We know that P1 is what we don't know. We know Z1. We know this height here. This would be Z1, right, in this case. And this would be Z2. So we know each of these. And so we also know this. We know that if you look at drawing an arc, so what we'd like to do here, when we look at this portion, we'll draw an arc which is, and here. And this would be the magnitude of r. If we draw an arc for this particular trajectory here, then the radius of this is infinite radius, right? This is normal to the streamline coming down here. This is normal to the stream, well, let's do it here. This is normal to the streamline coming down here. And this is normal to the streamline coming down here. It's of infinite length. It goes an infinite distance. And so we know that this term here is infinite. So this is infinity. This is infinity. And so these terms go to 0. And so if we just rearrange that, we end up with P1 is equal to Z2 minus Z1 times unit weight. Z1 is more positive than Z2, And so the pressure at Z1 is equal to just H times unit weight. So nothing more than what we understand about this system already is that the pressure distribution in this should be just the same as if it's a static fluid. And it conforms to our idea of dividing this into elevation head, pressure head, and velocity head. So now it gets a bit more complicated if we look at this system here. So let me get rid of that stuff. I don't like to remove it, but we need some space to do it, and you can grab it online once it's posted anyway. And so let's do the same thing as before. So we're going to write this expression between these 2 points. We'll choose point 3 and point 4. How do they do it below? They do it point 4. They do point 4 on the left-hand side. So let's do it in unison. The pressure at point 4 plus density, the velocity squared at 4 divided by the radius of curvature, this differential magnitude, the unit weight Z4 is equal to P3 plus the same term, density, integral V3 squared over R dn plus unit weight times Z3. So what do we know? We certainly know these two, just from the elevation. The difference between them would be the same as these if we look at continuity, but we don't need to worry too much about that. We know some radius of curvature R, so we have this, which isn't 0 now, it's or infinite now, it's some finite value. We know that P4 is atmospheric, and so we can set that to 0. And we know that the value we want to probably get, which we don't know, is P3. It's the only one we don't know. We have a streamline velocity, which the velocity that we're talking about is always a streamline velocity. So this would be V3, and this would be V4. We know from this system here that this is jugging along. We can define based on what we'll call continuity. Mass in equals mass out. We can make the case that flowing along here, the velocity has to be the same on all the horizontal streamlines that go through here. So we know that these are the same, and there's some value Vs. And so we can rearrange this in terms of P3. I'll go back red again. Is equal to unit weight Z4 minus Z3. Right? Just taking this term here on the left-hand side. And it's going to be these other two terms plus this integral V4 squared over R dn minus V3 squared over R dn. So this is going to be exactly the same as before. This is just going to be a linear distribution of pressure. This is bigger than this, and so the pressure at this point is just going to be the depth below. But there's an extra term here that complicates matters. And so what we need to do with this is just realize that each of these terms we can simplify. And if we write that out in longhand, then these two terms together would be the integral from R equals 0 to R equals whatever. So this would be, for this term, 0 to R4, and whatever is in there, minus the integral 0 to R3, again of the term that is in there. And if you think of what an integral is, an integral R, some function f of R, it's just this. So the integral to R4 is just this area under the curve here. The integral to R3 is this area under the curve here. If you subtract one from the other, then this is just equal to the same integral, R3 to R4. The velocity squared is constant, we've just said. It's divided by a radius. We hope that the radius is big compared to this distance in these. And if that's the case, we can take this as a constant. And then this term here. And the only thing we have to worry about or wonder about is the value of this component here. We said originally, if we go back up here, that when we define this geometry, did I do it today? I went far too far back. That this normal to acts normally in towards the center of rotation. And so we have to honor that. So we noted this form before. And so what we can do is we can just change these lengths. In this particular case, we'd probably think of this magnitude here as being, I'm running out of space, whoops. We could think of this as being dz. So in other words, dz is equal to minus dn. And so we can substitute this with minus dz. And if we do that, then we end up with an expression which is this here. P3 is what we had on our left-hand side. This is the unit weight, which is the difference between these two pressures, which is this. And when we do this integration, we don't do it between 0 and R4 and subtract. We just do it between R3 and R4. And actually, these are just Z3 and Z4. So it ends up being the same characteristics as here. And if we do that, we end up with this expression here. This is kind of the average radius to our point. So it's some given value. We're making the case that R goes a long way down, and so R3 and R4 are basically the same number. They don't differ by very much. I suppose you could take the average between them, but we've just tried to simplify matters. But what this tells us, I guess, which is important, is that if you just look at in terms of what this means, it's saying that the pressure at point 3 is equal to the hydrostat. So if you go down with depth, this is minus z. This is point 4. This is point 3. Then by definition, what it's saying is that there's a hydrostat that goes down. This is given by this term here. But there's a term which is less than that. This is always positive because it's the velocity. Actually, it makes a difference. We use the clockwise thumb rule or whatever. That this is the x-axis of rotation. The directions of your fingers are always positive. It doesn't really matter because the rotational velocity is squared. And so positive or negative, it always ends up to be positive value. R has to be positive, and density is always positive. So this whole term here, by definition, has to be positive, and so we're subtracting it. So what it's saying is that as you go to this particular point here, the pressure at point 3 has to be less by some amount, and that some amount is equal to this expression here. And so it's exactly what you'd expect. You're going down the road, you go over a bump. If you go too fast, you catch air on your bike or the car, hopefully not for very long, and you feel weightless, actually, briefly if you catch air, right? That's, by definition, that's what you're doing. As you accelerate up an interior curve, you feel like you get pushed into your seat because there's a reaction of your centripetal force against the road. And of course, if you look at what's going on in this particular case here, that's exactly what's happening, right? So it's no different than if it's a fluid. It could be fluid in a car, but it's going around here. If you squirted fluid along this flume, it would tend to do exactly the same thing. It would hug the curve and come down the other side. If it wasn't fast enough, it would just get higher up, then fall back on itself. But if it's fast enough, it would go around the full thing and it would do the second loop as well. And so, merely to make the point that fluids really aren't very different from solids or mechanics. It's F equals ma, and in terms of centripetal acceleration, pressures normal to a streamline given by Bernoulli just respond to that. Okay? And you could do exactly the same if you wanted to at this particular point here. Right? If you wanted to do the calculation for 2 points which were right here, say point 0.5 and 0.6, then it would be exactly this. I guess it would be here, right? 5 and 6. This would be the radius to some center of curvature, r. And because this is upside down, now all of a sudden, the fact that if this were vertically upwards, this now is z. And so the direction normal to the curvature, given by this blue line, dn, in this case, dz is equal to plus dn, right? Because this is going into the radius of curvature, and it's in the positive z direction. This was going down into the radius of curvature, and z is upwards, so they're against each other. And if you did the same calculation, you'd find out that all that would change would be that the magnitude, the magnitude of this term here would merely be positive. So that as you went across that bump, you'd feel that you're heavier otherwise. Okay? So that's really what it is. So we've written Bernoulli perpendicular streamline. If you want to look at it, this is a kind of a blow-by-blow evaluation of that process. So you can look at that. And so ultimately, in what we'll do in this class, the two expressions we'll use are this for along a streamline. I always tend to write them normalized by unit weight. Across a streamline is the one that we've just looked at. They exist in two different forms. These are the full terms of Bernoulli, if you like. We can also define them in slightly different forms, which are these differential forms, which we might want to use sometimes, but rarely. And that is these other two cases like here. But typically, we'll use them in these full forms. Okay, what else to talk about? Not sure. There are a couple of examples. Well, yeah, we've made this point before, what Bernoulli means. I guess it might be worthwhile talking about stagnation, because it came up in some of the questions after 4.2. Yeah, we have the jet engine over here. We have the truck over here. How do you define your boundary conditions? Well, this is definitely a stagnation point, right? This is point 1 and point 2. By definition, what's physically going on is when you look at Bernoulli, this pressure, this velocity which comes out here is the only term that's relevant. Elevation is 0 and the pressure is 0 for the points we made. And this has to be equal to a 0 velocity here, and therefore the only appropriate term is this. So the expression we get is just this. And the reason for this velocity is that it's coming at you, it hits you, and it has to skew off to the side. And so this is what we refer to as a stagnation point. If we wanted to, we could look at the behavior at this point here. So this would be point 1. This is what we've called point 2. And this is point 3. Of course, we can write Bernoulli between this point and this point if we want. But if we do that, all it will tell us is that the pressure here, the velocity here is the same as the velocity here, because the pressure at these 2 points have to be the same. And so that's not very useful. What is useful is if we write it at places where we think we have dissimilar conditions, and out of the 6 variables we have, 3 upstream, 3 downstream, we hope that we know 5 of them, and if we know 5 of them, then we can calculate one that we need to know, which in this case was this pressure. A couple of examples, you can see them in previous videos if you want. A loon's diving into the water. What is the pressure on its beak? I guess the other thing that we might mention, I suppose, is that Bernoulli, we said the requirements were that it has to be steady, incompressible, irrotational, and inviscid. So inviscid means no viscosity, but we've already said it works in air and in water. Water has quite a high viscosity. It already works in compressible fluids to some degree because it works in air as well, which is quite compressible. But the steady condition is perhaps the important one. This condition for the jet engine was steady, right? You look at the velocity here at time 1, it's 500 miles an hour, 200 miles an hour, whatever we said. You look 10 minutes later, it's still the same. You look at the velocity here at 0 time, it's 0. You look 10 minutes later, it's still 0. So that's steady state. But if you have, for instance, in this example here, you have a bird, I can't draw it very well, but I'll draw it like this. This is its beak, diving into water, which is what this question is about. Then if you look at the velocity here at time 0, then it's 0. But if you look at the velocity here as the bird's beak goes here, initially it's 0, but then it's being pushed aside by the bird. And so this scene, if you like, is changing from time 1 to time 2 to time 3, etc. And so we can't use Bernoulli to solve that. So what we do is we just change our frame of reference. We change our frame of reference so the bird is static and the water is moving and hitting it in the beak. And this way the velocity far away is equal to the speed of the bird, which is static. And as it hits the beak of the bird, the velocity is 0. And then we satisfy the condition of steady state. So that's the behavior. So you can look at that. You can look at going off the top of Niagara Falls. It's just the same as the example we've just done. But you can, and those are online and solved online if you want to look at them. Okay?